Welcome back, everybody. This problem is dealing with work and energy and the law of conservation of energy. And it's a pretty tough one in that there's a lot of changes that take place, but we're going to break it down in such a way as to see that really this problem is just like any other energy problem where we set up conservation of energy. So reading through the description, we've got this fairly complicated path that this little block is going to go through. So we see that it begins over here at rest. It's compressing this spring right now. So there must be somebody holding on to that thing right now and keeping it in place. We're going to release it, and it's going to shoot over here across this 1 meter stretch where there is friction. The rest of this surface is frictionless, it looks like, but during that section we do have friction. So we're going to be slowing down over that. Then we're going to go up this ramp and off this is a frictionless ramp, and then off the ramp, sailing through the air before we start to come back down somewhere here. So we're looking for some position right here where our block gets to its maximum height up here before it starts to come back down. While there are other methods of solving this one besides conservation of energy, at least after the initial section there, if we figured out how fast the spring makes this thing move, we could solve the rest using Newton's laws and the kinematics equations. We're actually not going to do that here, but it is an option for you. We'll set everything up, though, in terms of energy. So let's think through the energy and the important moments here. We've got, to begin with, let's just label important moments. So let's call this time A. That's when the box is compressed or compressing the spring as much as it can. And then time B is going to be a very short time later after our spring has been returned to its original shape. And so our block is moving there. Our spring is no longer deformed. Point C is going to be right here at the end of this frictiony area of the surface, so we will have slowed down a little bit. Part D is going to be right here as it's leaving that ramp, and then part E is going to be up here at its maximum height, and we are looking for the Y position here. That's our ultimate goal on this one. So I think it's useful to go through this and think about the type or types of energy that are involved in each one of these moments in time. So at point A, we don't have any motion at this point. Our block is as low as it can get, and we haven't had any friction or any other forces acting on this thing. So at this moment, we really have a simple picture for energy. All we have is spring potential energy. At point B, we've got now some motion. Our spring is no longer compressed. We're still as low as we can get. We still haven't had any friction at this point. So we have nothing but kinetic energy at that point. So we could solve for, say, how fast we're going at that moment. After point C, or after it's gone through this section from B to C, we still have some speed, so we're still dealing with some kinetic energy. But we've also had some work done on this box by friction, so I'm going to include that. And that needs to be a part of our problem throughout here. So some of our energy has now been turned into, well, mostly heat as a result of this friction section. At point D, we have our block still moving. It's going off the ramp, so we still have kinetic energy. We still had some of that energy that was lost due to friction or transferred to another form due to friction, so I'll include that here. But now we're up at some height, so we have some gravitational potential energy up there. And then at point E, we have more gravitational potential energy up there, but not to the point where we have no kinetic energy. It isn't moving up or down at that point, but it is still moving over to the right. So we still have some kinetic energy. We still have that energy that we have to account for that was transferred due to friction. And we have some gravitational potential energy. So we have less kinetic energy and more gravitational potential energy, but still a little bit of each. So we could break this up into these 5 different moments and solve for everything, solve for the speed and the position at each moment in time. We'll find that we won't have to go quite to that extreme, but not too far off either. So we know that the total energy throughout this whole problem has to be the same. Ultimately, I started over here with just spring energy, and by the end of that problem, that's going to be converted into some work due to friction, some amount of kinetic energy, and some amount of gravitational potential energy. And this is the term I'm going to be looking for at the end, because that'll have, if we write that as m times g times h times the height of the object, that'll have the value, the variable that I'm looking for at the end. So I want to get to this point. I know the total energy has to be the same throughout, so I can figure out total energy since I know everything at the very beginning. And I can set the sum of these 3 energy types equal to the total energy. Work from friction, we can calculate. That'll be a force times a distance. Kinetic energy, well, I know that it's just going to be moving to the right at that point, not up or down. So I'm going to need to figure out, how fast to the right it's moving at that point. Now to figure that out, I'm probably going to come back to this point where it's just leaving the ramp and figure out, how fast at this 30-degree angle is it moving at that point, and then break that up into x and y pieces. So really quite a bit to do on this problem, but we'll just break it up into steps, and every step of the way it's just about energy conversions. So let's start with that very first moment, moment A, where I have nothing but spring energy. I can calculate spring potential energy by using the equation 1/2 kx squared. Be careful when you're drawing this out, that k is a lowercase k, and it means the spring constant, not kinetic energy. So I'm given each of those values. The spring constant is 2,500 newtons per meter, and that thing has been compressed 0.20 meters, and don't forget the square on that one, and that gives me a spring energy at that point of 50 joules. Now that is the only form of energy that we have at that moment, so later on in this problem, our total energy we're going to be able to set equal to 50 joules. Now I know that at point B, I still have the same total amount of energy. It's just been changed from spring energy into kinetic energy. And so really I don't need to do much there. Maybe they would ask me to find the speed at that point here, but in this question I don't need to solve for that, so I can kind of skip over part B there. I do want to know how much work I have done on this thing due to friction, because I know that back up here, that's a term I'm going to be interested in. So work due to friction. So let's calculate that next. Now work is going to be equal to the force times the distance times the cosine of the angle between those. I think it's useful at this point to make a sketch of what's going on there, both for the force and for the displacement vector. And before we move on, let me just add here that US, the spring energy, I'm later going to refer to that as the total energy for this system, 50 joules. So just so I don't forget about that. Okay, so now we've got friction acting to the left on this block, and it's going to be traveling 1.0 meters to the right. So the work due to friction for this section is going to be equal to the force of friction times the distance times the cosine of the angle between the force vector and the displacement vector there. So the work due to friction then is going to be equal to, oh shoot, I don't know the force of friction on this one, but I do know that I could calculate that as mu times the normal force times d. And then I'm just going to go ahead and plug in here. I know that friction is to the left, displacement is to the right, so that's a 180-degree angle between those two. So cosine of 180 degrees. And then, oh gosh, I don't know the normal force now. I know mu, but I don't know the normal force. But hey, it's sliding across this horizontal surface. It's not accelerating upward or downward. So I could figure out, yeah, up and down forces must balance each other. So the upward force must be the same, the upward normal force must be the same size as the downward gravitational force, which has a value of the mass times the acceleration due to gravity. So the work due to friction, then, I can write as mu times m times g times d times -1. Cosine of 180 degrees is -1. And I'll plug in everything I know now. Work done by friction is equal to mu, that was 0.25, times the mass is 3 kilograms. Acceleration due to gravity is 9.8 meters per second squared, times 1 meter, times that -1 from the cosine of 180 degrees, and that gets me the work done by friction being equal to a negative 7.35 joules. Now, we can take that number then and figure out what our new total energy is going to be. We know that work is equal to a change in energy for our system. So we've just had the ramp do, the surface here, that horizontal surface, do negative 7.35 joules worth of energy on our system. So that means we've taken away 7.35 joules of energy. So we started with 50 joules, and we've taken away 7.35 joules. So our new total energy is going to be equal to our starting 50 joules plus a negative 7.35 joules, which is going to get us 42.65 joules. So that's our total energy after we get past that section where there's friction. So now I don't need to worry about including that work term anymore in my calculations. I just need to know all my energies add up to 42.65 joules, not up to 50 joules. So let's move on to the next section. That was for the space between B and C. So I could figure out how fast it was moving at point C. I just set the kinetic energy equal to 42.65 joules. Not necessary here though. Instead, I care about how fast it leaves that ramp at. So at that point, it has both kinetic energy and gravitational potential energy. So let's set that up next. So at point D, we've got a total energy still of 7.35, oops, that's not right, 42.65 joules. And at this point, that's made up of, a little gravitational potential energy. We're 0.5 meters above that lowest point. So we got some UG, and we're still moving, so we've got some K, kinetic energy. So we can solve for one of those by plugging in expressions for each of those. So 42.65 joules still is equal to a UG, I'll do as M times G times H, plus kinetic energy is 1/2 times M times V squared. Now I know everything in that expression except for the speed. So I can plug in for the speed at which this thing leaves that 0.5 meter tall ramp. So 42.65 joules is equal to 3 kilograms times 9.8 meters per second squared times the height of that ramp there is 0.5 meters plus 1/2 times 3.0 kilograms times the speed squared. So we'll do a little algebra and plug into the calculator, and we'll solve for speed, and we get an answer here of speed equals 4.3 meters per second. And that's at point D. I'm just going to add a little subscript here so I don't forget where that is. Now that 4.3 meters per second, that's parallel to the ramp, so it's up and to the right. I know that the speed to the right isn't going to change, because after it's leaving the ramp, it behaves like a projectile. And you could solve the rest of this problem just with projectile motion. We'll solve it using energy, but there are multiple ways to do this one. So we need to figure out how much of that energy is going to stay as kinetic energy. The energy that stays at kinetic energy is the energy associated with that right and left motion, because that's not going to change here. At the very high point, it's not moving up or down. It's still moving to the right, though, at the same speed as it leaves the ramp. So let's figure out what that part of this velocity is. So we've got 4.3 meters per second as we leave this 30-degree ramp. So we need to find the x component for that. That's what we're interested in. Vx. So then v dx is equal to the hypotenuse, 4.3 meters per second, times the cosine of 30 degrees. So v dx is going to be equal to 3.72 meters per second. So even when it gets up to point E, it's still going to have some kinetic energy. We can figure out how much by knowing that it's still moving to the right at 3.2 meters per second. So at point E, the total energy hasn't changed from what it was a minute ago. We haven't had any more work done on our system. So the total energy at point E is still going to be equal to 42.65 joules. And at point E, that thing is both moving, so it has kinetic energy, and up higher than the zero height we defined, so it has gravitational potential energy. So that 42.65 is divided between those two forms. So UG at E and K at E. And then we can write that as 42.65 joules is equal to mgh, height at E, plus 1/2 mv at point E squared. All right, now in this equation I've got mass is given to me. G is 9.8 meters per second squared, I know that one. And the speed at point E, well, when it gets to its highest point, remember it's not moving up or down, it's only moving to the right. So that was what we were doing earlier here with finding the x component of that velocity. That's how fast it's still going to be moving at point E. So we actually know everything in this equation. So let's plug in for all we know. 65 joules equals mass is 3 kilograms times 9.8 meters per second squared times the height at E plus 1/2 times the mass, which is 3 kilograms, times, oops, I'm running out of space here, 3.72 meters per second, and that gets squared. And a little rearranging with algebra and solving for height, and we get the height at point E is equal to 0.74 meters. That is the final answer that we were looking for. Now, again, you could solve this one either differently by using dynamics for the part where it's slowing down, so Newton's second law where it's slowing down, figure out how fast it's going to go at the end of that, and then at the end of the one meter section, and then figure out the acceleration on the ramp to figure out how much it's going to go as it's leaving the ramp, and then use kinematics for the last part. This way is definitely fewer calculations, so probably faster, probably, once you're used to it anyway, easier to solve this way as well. But again, the idea is just that the total amount of energy can only change when we have work done by some outside influence here. So our system is the block and the spring and the ramp and the earth, and then the only outside influence we had was friction from that section of the flat piece there. So that was the only time our total energy changed. Decreased from 50 joules to 42.65 joules, and then can be divided up differently in different forms of energy. I think it's useful to approach these problems by first considering the type or types of energy present at each point, and then think through the work done on that, so how the total energy might change. Figure out what the total energy is at one moment, and then kind of work your way through from there. Well, thanks very much for watching, folks. I hope you found this useful. If you did, I'd encourage you to subscribe to this and check out some of the other videos. And if you have somebody else in mind who might find this useful, recommend it to them as well. Thank you much.